I'm going to describe how to use an interactive simulation that models single-stage batch distillation. The simulation display looks like this, where we have the option. In this case, we're showing a Txy diagram. We also can look at an XY diagram, or we can look at the flasks that are collected. So we start with a liquid and a still. The initial mole fraction in this case is 0.5, and this is the mole fraction, the more volatile component. And then each distillate flask that we collect contains 0.1 moles for the disposition of the slider. What the simulation does is show how the composition changes as we collect additional flasks, and then that's also displayed on the Txy diagram, where we can see how the temperature changes, and the temperature is displayed directly on the still also. Well, the idea is that we collect in this flask a mixture that has a higher mole fraction of the more volatile component than that which is in the still. You'll notice that a little faint to see, but we have no azeotrope for this particular. We're just looking at an ideal solution, but we can also select azeotrope. So let's look at the simulation, observe the behavior as we collect samples. So here's the simulation. You notice we're given some directions. Let's set the mole fraction of 0.49 in the still, and let's evaporate 0.25 moles with each flask collection. So starting with no azeotrope, if I click collect, then we see that the flask fills up. The mole fraction 0.72, it's decreasing as we evaporate more, but we start out with a mole fraction of 0.49, the more volatile component, and we have mole fraction in this distillate of 0.7, and of course we decrease the mole fraction in the still. We can collect another flask, and you'll notice the temperature is going up as we collect the flask, and the mole fraction of the more volatile component is going down as we deplete it in the still. The simulation is set to stop when we get to 0.01 moles in the still, or if we were to collect a small amount each time, when we get 8 flasks collected. Now for this process, we could look at the Txy diagram, and let's reset and see what happens. So the Txy diagram displays the same behavior as we see here. The temperature is going up as we distill more of the liquid, and the mole fractions of both the liquid and the vapor phase are decreasing. Well, we could also look at an XY plot and again watch the mole fractions decrease as we collect. It's a little hard to see here. We have no azeotrope selected, but we could, if we reset, we can select the maximum temperature azeotrope, and let's move away from the azeotrope to start. And then as we collect, just like we saw for the ideal solution, the temperature is going up, and this means the mole fractions are approaching the maximum temperature, which is the azeotrope. So the mole fractions X and Y are getting closer to each other, and of course for this condition, notice the mole fraction of distillate is less. Let's switch over. We can see the mole fraction, we started with 0.24 for the more volatile component, but the mole fraction is only 0.15 here because we have a maximum temperature azeotrope. We could also select a minimum temperature azeotrope, and if we do that, let's look at the Txy diagram, we'll see that as we start collecting, temperature goes up, so we're moving further away from the azeotrope. So hopefully this single stage batch distillation gives you a little better understanding of this idea of batch distillation, because often we're going to have a number of stages here to get a better separation than we have from just a single stage.